Okay, so, we have been looking at inheritance hierarchies, uh, and we have seen that we have defined the notion of an admissible path, and admissible path is something that you can believe in. But when we started looking at the inheritance hierarchy, we saw that there could be networks which are inherently ambiguous essentially. Now, in such situations, what are the set of beliefs which you are willing to subscribe to, or which is a set of beliefs that you think are credulous essentially. So, in some sense now we are entering this, moving away from this neat and clean first order logic kind of representation. This thing we are talking about real world situations where you have to choose between conflicting beliefs essentially. So, we are moving towards belief, and we will spend the next few lectures looking at the logical approach to belief, but today let us focus on the inheritance networks. So, we have this inheritance hierarchy. Tau, which is made up of a set of n edges, and we have this notion of path in the network essentially. We are we will start with some definitions. We say that inheritance hierarchy tau is connected, or it is A connected if there is a path from A to every node in V essentially, or in tau essentially. So, with respect to an A, we say that tau is A connected if there is a path which goes to every other node essentially. We say that tau is ambiguous if it supports A dot A V and A not V. And we have seen that this is possible essentially. So, we can say that a penguin is a bird or is an aquatic bird, and so if you are given only this, then it is an ambiguous network. You could have both the paths are admissible as you can see essentially, nothing gets preempted, or there is no redundant edges and everything essentially. So, we define the notion of an extension, a credulous extension of tau is a sub hierarchy or sub network So, again everything is with respect to an individual A. That is maximal and unambiguous. And what do we mean by this? That adding anything any edge would make it either ambiguous or not A connected. So, that is maximal, unambiguous and A connected. So, we are interested in a sub graph or a sub hierarchy which is unambiguous, which means it does not support conflicting conclusions, which is A connected, which means that everything in that sub graph is something that you are going to be willing to believe about A, and it is maximal in the sense that you cannot add anything else to that essentially. So, let us look at an example. Supposing the graph that is given to you is that there is something called platypus, which is an egg layer, which is a furry animal, and furry animals are generally mammals, but egg layers are not mammals, and mammals are generally milk producers. So, you can see that this is an ambiguous network. It is also a maximal network, because every node in this network has a path. So, if you look at milk producer, there is a path which goes from platypus to furry animal to mammal to milk producer essentially. But this is not a credible, I mean this is not credulous, because it is ambiguous essentially. So, we do not know whether we want to say that platypus is a mammal or whether platypus is not a mammal essentially. Both are supported in this. So, if you look at the notion of admissibility, you will see that both paths are supported. So, this has got two extensions, or two credulous extensions. In one, platypus is a milk producer because it is a mammal, and it is a mammal because it is a furry animal. Also, this what I have drawn so far is not maximal, because we also know that platypus is an egg layer. So, this is one credible extension. Platypus is an egg layer, platypus is a furry animal, it is mammal and it produces milk. The other extension is that it is an egg layer, and egg layers are not mammal, but we know that it is a furry animal. So, the claim is that both these sub hierarchies are credulous extensions. What do we mean by that? That they must be maximal A connected unambiguous sub networks essentially. So, what have we removed in this thing we have removed this edge black edge which is not here, and in the second one we have removed one black edge here and another black edge here. So, let us look at these 3 examples and see whether we can add those edges essentially. So, if you look at the network on the left, if we add that black edge, then this one makes it ambiguous. Which is also the case for this. But if we add this edge only, so only adding what is the problem with that? That it is no longer A connected. Remember, I am saying that only adding this edge essentially. So, which means you do not add the starred edge, only the double starred edge. If you add to the network on the right, then there is a sequence of edges which is not a path, because it has got a negative edge in between essentially. And remember that a negative path can only have a negative edge as the last edge essentially, and because that is not the last edge, that is no longer an A connected network, which means there is a node in that from which to which there is no path essentially. So, both these networks which you see the red part of the networks are maximal A connected unambiguous subgraphs essentially. So, you can take either view, you can either take the view that platypus is a mammal and therefore, it is a milk producer, which will be consistent with what you know, or you can say that it is not a mammal and then you can leave it there essentially. It is a furry animal, but it is not a mammal essentially. So, this gives us a mechanism for trying to get a consistent set of beliefs about an individual, so which we call as a credulous extension, that okay, all these things are true about A essentially. So, but there is more than one consistent set of such beliefs, or there is more than one credulous extensions as we saw. Now, sometimes a network may be inherently ambiguous in the sense that there may be nothing you can say, and remember we are only looking at the topology about whether one of them is a better extension or not, but sometimes there can be a notion of a preferred extension. So, if there is more than one extensions, then one of them may be preferred. So, let us work on this with an example here. So, this example is simple, which is the elephant example. So, elephants are gray and let us say Clyde is not gray. So, this is our knowledge base. It has got 3 statements in it. Clyde is an elephant, elephants are gray, Clyde is not gray. All these 3 statements result in this network that we have. This has got 2 extensions, because you cannot believe everything in this network essentially, because there is a path. I mean, if you took the well, essentially this is not a maximal A connected subgraph. So, if you chose a maximal A connected sub network, we would get 2 networks. One is gray elephant, Clyde, and it is no longer ambiguous, and the other is Gray, elephant, Clyde. So, we have two credulous extensions. One is the red one, which is says that Clyde is an elephant and elephant is Gray. The other one says that Clyde is a elephant and Clyde is not Gray essentially. But in that second extension, we do not believe that elephants are Gray. But remember that this extension is with respect to A essentially. These credulous extensions are with respect to a given individual. So, we are talking only with respect to Clyde. So, in some sense the second extension, which is the one in blue, says that elephants are not Gray, because we know that Clyde is not Gray in some sense. The first extension, which is in the red, says elephants are Gray, but of course, it forgets the fact that Clyde is not Gray. In fact, we have removed it from this thing essentially. So, which of them is the preferred extension? So, let us give first. So, let x and y be credulous extensions of some inheritance hierarchy tau. We say that x is preferred over y, it is a preferred extension if there is. So, I keep forgetting to write an edge, that these are all with respect to some individual A. So, if there is an edge which is v dot x such that x and y agree till v, and v dot x is inadmissible and v dot x is in y. So, instead of v dot x, we could have also have v dot not x, we treat them equivalently. Here also you could have v dot not x. Essentially, it is an edge which is not admissible according to the definition of admissibility that we have, and it is there in one of the extensions essentially. So, the extension in which that inadmissible edge is there, that extension is not preferred. So, in this case it has to be in y and not in x essentially. So, what is the edge we are talking about in the example, and which one is x and which one is y, which extension is x and which extension is y. So, if you look at the original tau. So, this is tau, right, and these are the two extensions of tau essentially. So, if you look at this tau which says Gray, elephant, I will just write elephant here, and Clyde, I might as well write it. We saw that this edge is not admissible. Why is it not admissible? Because it is preempted by this negative edge essentially. Remember the definition of edge being not admissible, that its conclusion should not be preempted by something which is in the path. An edge is admissible if there is a positive path leading up to that edge and there is no node in that positive path which preempts its conclusion. So, this edge elephants are grey has a positive path leading up to elephant, which is Clyde is an elephant, but there is a node Clyde in that positive path which preempts this conclusion that elephants are grey essentially. So, there is a preemptor of this edge and therefore, this edge is not admissible, and this edge as you can see is present in the second network here and the first network here, which says that elephants are grey. So, in according to our definition this is y and this is x. So, this is a preferred one. So, of the two credulous extensions that we can construct for this small inheritance hierarchy, both are credulous in the sense that both are not inconsistent essentially. The networks, the sub networks, we are not talking about consistency with respect to the original knowledge base, which anyway is inconsistent in the sense that if you say elephants are grey and Clyde is an elephant and then you say Clyde is not grey, obviously that is not inconsistent. If you wrote that thing in first order logic, you will immediately be able to draw a contradiction or a null clause or whatever depending on the method you are using. But we are talking about general statements, we are not talking about universal statements here. If you say that all elephants are grey and Clyde is an elephant, then you cannot say that Clyde is not grey, because that makes it inconsistent. But given this knowledge base that elephants in general are grey and Clyde is an elephant, but Clyde is not grey, there is nothing inconsistent about it. You can have two sets of belief. One says that Clyde is an elephant, so he must be grey. So, the information about Clyde not being grey is no longer valid, or you can say okay, we are talking about Clyde, we know that Clyde is not grey and but we know that Clyde is an elephant. So, we cannot believe at least as far as Clyde is concerned that elephants are grey essentially, which is the preferred extension, because it is consistent with the fact that we know that Clyde is not grey essentially. And the definition of this preferred extension simply relies on the fact that it does not contain any edge which is inadmissible and which is not in the other. So, it is not necessary that there may be a preferred extension. Maybe as a small exercise I will ask you to construct some example in which there are two extensions and none of them is preferred over the other. A network X in this case is preferred over a network, a credulous extension X is preferred over a credulous extension Y if Y has got an inadmissible edge which is not there in X. But you can create an example in which there is one edge which is in X and not in Y, and which another edge which is in Y, but not in X, in which case neither is preferred over the other, or both are preferred over the other essentially, but that does not make sense. So, we say that none is a preferred network. So, finally, we can talk about inheritance again. What can we believe about an individual? So, people have identified three kinds of reasoning. The first kind is called credulous reasoning. It says choose a preferred extension and believe whatever it says. That if there is a preferred extension, and there could be more than one preferred extensions, if there is a preferred extension, choose one and believe whatever it says essentially. So, that is credulous reasoning. You are willing to believe anything which is for which there is some support in the system. Then we have skeptical. This says that believe the conclusions that are supported by any path that is present in all the preferred extensions. So, essentially what skeptical reasoning is saying is that if all preferred extensions have a particular path which supports something that I am trying to believe, that A is an X or something like that. If all preferred extensions have a path, have the same path, then I am willing to believe that A is an X. And the third one, which is slightly different from the second one, some people call it as ideally skeptical. Believe the conclusions that supported in all preferred extensions. So, both B and C, both skeptical reasoning and ideally skeptical reasoning, they say that all preferred extensions must support this particular fact, that A is an X, that Clyde is grey or Peppy can fly or whatever essentially. All credulous, all preferred credulous extensions must be there. So, this preferred is important in both these. In fact, in all the three, preferred is in the first case, any preferred in the credulous extension, any preferred extension you are willing to accept, but for the B and the C cases, this all is important. All preferred extensions must support this fact. Now, C does not care about what is the path which supports the fact, as long as it supports that fact, that conclusion, whereas B is really skeptical. It says that it must give the same reason, that A is x 1 and x 1 is B must be present in all the paths. That same path must be present in all preferred extensions essentially. So, there is subtle difference between the two, but essentially skeptical reasoning says that there must be consensus amongst all preferred extensions, whereas credulous reasoning is willing to believe any preferred extension and say this is what is true about the world essentially. Now, this kind of reasoning is very different from what we started with when we talked about knowledge representation reasoning. We said that we are talking about inference and deduction and what necessarily follows and things like that. Now, suddenly we have, through this journey, we have come to a state where we have a knowledge base which supports multiple viewpoints essentially, and now we are talking about what can we believe in essentially. So, we are talking about belief systems and things like that essentially. So, this analysis that we have done with this inheritance hierarchies is basically topological graph based analysis, which says that if this is the inheritance networks, then these are the kind of things that you can believe about in particular individual essentially. In the next class, we will try to go back to a logic like formalism, and we will try to see how can we extend logical mechanisms which will allow us to reason with general statements. Okay. So, the key difference between what we are doing in inheritance hierarchies and deduction is that in the deductive systems that we talked about, we had only universally quantified statements or existentially quantified statements, but a universally quantified statement, which is the kind of generalizations we were talking about, applied universally. When we said all men are mortal, it applies to each and every man essentially, or each and every human being essentially. But when we say birds fly, it is not a universal statement, but it is a general statement essentially. It says that in general, in some sense birds fly, that okay, most birds fly or something like that. So, people have tried to do probabilistic reasoning about these kind of things, that what is the probability that bird would fly, but we are not getting into probabilistic reasoning here. We are trying to say is that in the absence of anything else that I know, what can I conclude essentially. So, if I tell you that Pepe is a bird, then you would be perfectly justified in concluding that Pepe can fly essentially. But after some time, if I also tell you that Pepe is a penguin, and then I tell you that penguins cannot fly, then you would be justified in saying that Pepe cannot fly essentially. This is because we are not talking about universal statements, that we are saying that in general birds fly, but sometimes some bird may not fly. That could be because that bird is a penguin, or that could be because that bird is dead or something like that, or that maybe that bird is in a cage or something like that. We want to explore that sort of a reasoning essentially. So, we will in the next class, we will look at formalisms which will allow us to make those kind of inferences. And just as we talked about inheritance being diffeasible here, that reasoning also will be diffeasible kind of reasoning, and some people call it non-monotonic reasoning, which means you can draw conclusions which may not hold after you know something more essentially. So, as you know more things, some of the conclusions you may have to withdraw, some of the conclusions will be defeated essentially. So, that is called non-monotonic reasoning, default reasoning with similar words, and we will take it up in the next class essentially. Okay.